Good day, I greet to Dr. Haikar and all my teammates. My name is Yong Zhen with metric number 202454. We are from ECH 3120 Chemical Engineering Thermodynamics. Today, in this presentation, we will present about the general properties of gas. Right now, let me invite our teammates to introduce themselves.
Good morning, everyone and doctor. My name is Wong Sweet Yin with matrix number 202730.
Good morning, doctor and everyone. My name is QiuGe. My metric card number is 200072.
Good morning, doctor and everyone. My name is Steven Denzel Briones Cutad, and my metric number is 115.
Hello, doctor. My name is Siti, Hana, Alisa, binti Harun, and my metric number is 200634.
Hello everyone, my name is Haziq Isyraf Rosdi. Matrix number is 200816.
666. All right, doctor, to firstly give you the G's of our presentation, first of all, I would like to introduce the content. First of all, we have the thermodynamics properties, which is intensive and extensive properties. The second is specific properties, and the last would be equation of state. Will be further discussed with my groupmates. Now, let us define the thermodynamics properties. The measured thermodynamic properties are those that we obtain through direct measurement in the lab, and there are two can be defined as thermodynamic properties, which is intensive and extensive properties. Intensive properties, which includes pressure, temperature, and volume, and the other hand, extensive, which includes volume, enthalpy, entropy, and internal energy. So let us define intensive properties. An intensive property is a property of matter that depends only on the type of matter in the sample and does not change as the amount of matter changes. In other words, intensive properties are not additive.
Okay, thank you, Steven. So, doctor, I will continue with the intensive pressure and temperature. Intensive properties are properties that do not depend on the quantity of matter. Hence, pressure and temperature are always intensive, are written as capital letter P and T. Pressure is the normal force per unit area exerted by a substance on its boundary. Since pressure represents the force per area, the unit of Newton per meter square is most straightforward. However, in the context of the energy balance, we will be addressing in this text, the unit of joule per meter cube is often more useful. Temperature T is loosely classified as the degree of hotness of a particular system. On the molecular level, temperature is proportional to the average kinetic energy of the individual atoms or molecules in the system. Next, please.
Now, I am going to continue to define an intensive volume. Intensive volume can also be described as an intensive property, either as a molar volume, m cubed over mole, or specific volume, which has a unit of m cubed over kilogram. If a substance is distributed continuously and uniformly throughout the system, the intensive forms of volume can be determined by dividing the extensive volume by the total number of moles or total of mass, respectively. Thus, we would have volume over moles or volumes over mass, which is the indirect proportional, which is we can get the specific volume. Now I am going to pass. Oh, sorry. Now I am going to explain to you what is an extensive property, doctor. An extensive property is a property of matter that changes as the amount of matter changes. Like other physical properties, an extensive property may be observed and measured without any chemical change reaction occurring.
First, extensive properties is the extensive volume. The volume is related to the size of the system and it can be expressed in both extensive and intensive form. For a rectangular geometry, volume can be obtained by multiplying the measured length, width, and height. And this procedure gives us the extensive form of volume, which is volume in unit of meter cube or gallon. Next, please. Okay, the second extensive properties is the enthalpy, which is the first law of thermodynamics. Enthalpy H is the energy transfer between a system and the surrounding under constant pressure, and it is associated with both internal energy and flow rates. H equal to U plus delta PV. And we cannot measure the absolute enthalpy of a system, but we can measure the change in enthalpy for a process which can be defined as delta H equal to H out minus H in. We can develop this relationship between the temperature and enthalpy for an ideal gas. Application of the definition of enthalpy and the definition of an ideal gas give H ideal gas equal to U plus delta PV. equal to U plus RT equal to FT only, since PV equal to RT for an ideal gas.
So for the next thermodynamic properties for extensive properties, which is the second law of thermodynamic, entropy is the measure of a system thermal energy per unit temperature that is unavailable for doing useful work. The formula of entropy is S equals to Q over T. Because work is obtained from ordered molecular motion, the amount of entropy is also a measure of the molecular disorder or randomness of a system. According to the molecular concept of entropy, there are more molecular configuration accessible when a system has high entropy and also is disordered when it has low entropy and is more ordered. The equation of the change in entropy is delta S equals to S2 minus S1. The second law of thermodynamics states that the total entropy of a system either increase or remains constant in any spontaneous process. It will never decrease. Next slide, please. So the next one is internal energy. Internal energy is meant by the sum of the kinetic and potential energies of the particles that form the system. It can be understood in simplest possible ideal gas form. The internal energy of an ideal gas is actually proportional to its number of moles and to its temperature. The equation of internal energy is U equals to CV times N times T, where Cv is the molar heat capacity of the gas. The change of internal energy is delta U equals to U2 minus U1.
Thank you, my roommate, for explaining the thermodynamic properties of gas. So I'm going to explain the specific properties. So let us define what is specific property. Specific property of a material are derived from other intensive and extensive properties of that material. For example, the density of water is an intensive property and can be derived from the measurements of the mass of a water volume, and extensive properties, and divide by the volume, which is another extensive property. And there's another example, which is specific heat capacity, Cp, which is an intensive property and can be derived from heat capacity Cp, which is also an extensive property, and the mass of the system. Next slide, please. And now I'm going to explain another general property of gas, which is equations of state. So equation of state, EOS, is a series of thermodynamic equations relating pressure, volume, and temperature of a substance. There are few examples of equations of state, which are ideal gas equations of state, compressibility factor equations of state, QiuGe equation of state. And these equations of state are useful in describing the properties and the behavior of gases, as they provides very accurate result within a region. Next slide, please. So, so now we need to consider some properties in order to discuss the equation of state. The properties are P, which is pressure, V, volume, and number of mole of a substance, T, absolute temperature, R, gas constants, PC, critical pressure, VC, critical volume, TC, critical temperature, omega, eccentric factor, Vm, molar volume, D, compressibility factor.
Thank you, Sweet Yin. Right now, I will explain the equation of state. So right now, in this slide, we present two equations of state, which is the compressibility factor equation of state and ideal gas equation of state. First of all, we will start with the compressibility factor equation of state. As you can see, the expression of both equations is very similar. The only difference is the compressibility factor equation of state having an extra term of Z. The Z term is the compressibility factor. When the compressibility factor Z is equal to 1, then the equation will be simplified into the ideal gas equation of state. So the Z, also known as the compressibility factor, it is a measure of the extent to which the gas deviates from its ideal behavior. This factor can be obtained by calculating the the reduced pressure and the reduced temperature of the gas, and then the Z factor can be obtained by using the generalized compressibility chart. As for the ideal gas equation of state, it is the most simplest form of equation of state that relates the properties like the volume, temperature, and the pressure of a gas. And it has few assumptions, which is it assumes that there is no interaction between the gas particles, and there is negligible volume between the gas particle, and also it assumes that the gas particles move randomly in Brownian motion. Next slide, please. And right now we are showing a few cubic equation of state. We are showing four cubic equation of states, which is Spang-Robinson equation of state, SRK equation of state, van der Waals equation of states, and also Radich-Kwong equation of state. All these four equation of state is more complex than the ideal gas equation of state and the compressibility factor equation of state that we presented just now. Because of this equations complexity, we seldom use these equations in manual calculation. However, these equations is programmed in some thermodynamic software like Aspen and some process simulation software. This equation is very useful in calculating and predicting the behavior of a gas in real situation. Therefore, however, due to its complexities, therefore we seldom use it in manual calculation, but we more oftenly use this equation in computer software. Next slide, please. And until now, hereby that's all for our presentations. Hereby, I would like to thank all my group mates for putting their efforts in preparing in preparing the slides and making this presentation. And we would also like to thank Dr. Haiga for your lecture and tutoring. And that's all from us. Thank you and see you.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.